In this video, we're going to be solving a related rate problem of a type that kind of gives kids trouble, and that would be in the area of cones. In this particular problem, we have a tank of water in the shape of a cone, leaking water at a constant rate of 2 cubic feet per hour. The radius of the base of the tank is 5 feet, and the height, or the initial height of the tank, is 14 feet. In question A, we'll explore at what rate is the depth of the water in the tank changing when the water has a depth of 6 feet, and in part B, at what rate is the radius of the top of the water of the tank changing when the depth of the water is 6 feet. A good problem solving strategy here is to, number one, draw a picture, set it up, label it. So we have our initial dimensions of the tank, radius of 5, height of 14 feet, and then our water level, radius R, and height h. Well, what I know, or what's given, is that the rate of change in the volume is going to be negative 2 cubic feet per hour because, again, the water is leaking, so it is a decrease in water level. Likewise, we're given that we're looking for both the change in height and the change in radius at a time when the height is 6 feet or the depth is 6 feet, so I've got h equals 6 feet. What we're looking to solve for is the rate of change in height with respect to time and the rate of change in radius with respect to time. Now, a cone. Basically, you can think of the formula for volume of the cone from geometry as V equals base area times the height, or 1/3 base area times the height. In this case, the base is circular because it's conical, so I get 1/3 the base area, which is pi r squared, times h. When you derive that, you're going to have the quantity r squared times h, which is going to yield a product rule, which is going to give you both a dr dt and a dh dt and a dv dt in the same equation, and it can get really messy. So in cones, I try to avoid that situation, and I'm going to do that by setting up a little proportion. So what I know is that this value of the radius of the water at its height, so r is to h, as the original dimensions, 5 is to its height of 14. If you cross multiply, I get r times 14, or 14r, equals 5h. And from here I can set up two equations. One that will solve for r in terms of h, the other that will solve for h in terms of r. The first equation, to isolate r in terms of h, quite simply, all you do is divide both sides by 14, and you'll get the equation r equals 5 over 14, or 5h over 14. And to solve this one for h in terms of r, you just divide both sides by 5, and you get h equals 14r over 5. Now, we know the height is 6. I have an equation that relates r to h. I may or may not need to know the value of r, but since I've got the equation, let's go ahead and find it. That way, if I need it, I have it, and if I don't, no harm, no foul, you're set here. So I replace the h in the r equals 5h over 14 with the value 6, do a little basic arithmetic here, reduce, and I get, when the height of the water is 6 feet, the radius of the water is 15 over 7 feet. Now comes the fun part, the calculus. At what rate is the depth of the water in the tank changing when the depth of the water is 6 feet? Again, I'm going to take that equation we generated from the proportion, r equals 5h over 14, and what I'm going to do is take the volume equation, and everywhere in it that I have an r, I'm going to do a little substitution here and replace r with the quantity 5h over 14. What that does for us now is I have an equation for volume strictly in terms of height. It does not incorporate r in any way in it, and as such, the need for the product rule is negated. I won't have dr dt, I won't have to deal with that ndh dt, ndv dt. It's just a little simpler to deal with. So that's kind of my preference. If I square this entire quantity, I get that V equals, again, my 1/3 pi, 5 squared, 25, h squared, 14 squared, 196 times h. From there, let's start putting things together. 1 times 25 we know is 25. We've got our pi. 3 times 196 is 588, and h squared times h gives us an h cubed. Again, so what I have is an equation for V strictly in terms of h, so the need for the product rule is no longer there. It's just going to be a little simpler equation to work with. Let's derive. When I derive volume with respect to time, I get dV dt. Basic power rule, power 3 moves to the front. 3 or 3 over 1 gets multiplied by our coefficient, 25 pi over 588. And then your power of h cubed reduces by 1 to h squared. And then you have to multiply by your dH dt. Substitution, again, from what we knew at the beginning, dV dt was -2. 3 times 25 pi, 75 pi. 1 times 588, 588. Replace the h with the 6 from our original given statement, and times dH dt. So squaring 6 gives us 36. Everything else still the same. And now, before we start multiplying and solving and all that, I'm a big fan of trying to reduce while the numbers are still relatively small, as opposed to trying to do so when they get really huge. So I know that both 36 and 588 are divisible by 12. So I'm going to divide both those numbers by 12. 36 divisible by 12 gives me 3. 588 divided by 12 gives me 49. While they're not fantastic numbers to deal with, they are smaller than what we had. It'll make the reducing at the end a lot easier. So I get our -2 from dV dt equals 75 pi times 3, which is 225 pi, and then our 49 on the bottom, times dH dt. Now to isolate dH dt, you have a couple of choices. Number one, you can divide by the fraction 225 pi over 49, which I think looks messy. I'm a big fan of multiplying by the reciprocal, so to cancel a 225 pi over 49 being multiplied by dH dt, I'm going to propose that we just multiply by its reciprocal, which would be 49 times 225 pi. And you do that on both sides of the equation. Once you do so, you'll find that those cancel quite nicely on the right-hand side of the equation, isolating dH dt for me. And when I take the -2, or -2 over 1, times our quantity 49 over 225 pi, I get -2 times 49 is -98. And then on bottom I have 225 pi. Our units, feet per hour. There's your rate of change in height with respect to time. If you love decimals, have at it. It works out to approximately -0.139 feet per hour. If you're taking the AP Cal exam, know that they do typically go out to 3 decimals, so either answer would be acceptable. Part B. At what rate is the radius of the top of the water in the tank changing when the depth of the water is 6 feet? I can go and do my whole V equals blah 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 again, and this time I can substitute in terms of H in terms of R, or it's just going to be messy. Here's what I want to do. We had that equation we generated from our proportion as R equals 5H over 14. Well, if I derive that, I get dr dt equals my coefficient 5/14 times my derivative of height with respect to time dH dt. Well, we just found dHdt, so in essence what I'm saying is we can avoid doing the whole cone formula again and just substitute dHdt with what we found in the previous section of the problem, which we got, was it negative 98 over 225 pi, and we have this. No need to derive the volume formula and all that fun stuff again. Now, again, reduce if at all possible. 5 and 225 reduce. 14 reduces with the 98. So 5 divided by 5 leaves us with a 1. 225 divided by 5 is 45. Divide both of these by 14. 14 divided by 14 is 1. 98 divided by 14 is 7. And we've got a really workable answer here, nice and reduced. Negative 7 on the top, 45 pi on the bottom, gives us approximately negative 0.050 feet per hour. Thank you. I do hope that this helped.